Today, we're going to write our triple integral in spherical coordinates for the volume of our cone. We want the integral over the cone of the unitless function 1 dv. Remember that in this coordinate system, one of our coordinates is a distance, the other two are angles. So when we write dv, a small chunk of volume, I need dr, d theta, and d phi to all be distances. Unfortunately for our heroes, theta and phi are angles, so we need to use arc length to turn those into distances. dr on its own is a distance, so I could just use dr. d phi is an angle. That's the easier one to deal with because we see that the hypotenuse for the right triangle that uses phi has a hypotenuse of rho. So the distance from the origin is just going to be rho. So rho d phi gives us that side opposite. And so that gives us our distance. For theta, I need to use that top part, the side opposite phi with the hypotenuse of rho. So I need rho sine phi to turn theta into a distance. Because I want just the distance that gets projected down onto the floor where the xy plane is, or the r theta plane is. All right. So we're going to be integrating over the cone where we're just describing what's rho between, what's theta between, and what's phi between. We're going to integrate the function 1 with no units. The units are all going to come from dv, which is rho squared sine phi dr d theta d phi. So to summarize our dv, I've got my arc length factors, rho and rho sine phi. So I'm going to get rho squared times the sine of phi times dr d theta and dp. Now this might not be the order that we write our integral. We're going to make a triple integral, and the last integral, the one on the outside, that has to be constants. So it might be that it's more convenient for us to pick something, maybe what's, when we're picking our last integral, it's going to be that something that's easy to identify, an interval. It took me a long time to remember the word interval. I don't know why it took so long to do that, but it's not like I had to do arithmetic. It's not like I was trying to simultaneously run the arithmetic app and the talking app at the same time. There it is. All right. So since I want this whole cone, the easiest one to pick out for our last integral is going to be theta, because we want to go all the way around the cone. So theta goes from 0 to 2 pi. I want theta to go from 0 to 2 pi. That will take us all the way around the cone. So the easiest interval to pick out is theta. Since theta is just going to be between constants, theta is just going to be a nice constant interval, we'll use this one last. So we'll finish up this integral, the last one, the first one that we write, the last one we evaluate, the outside one. will be the integral from 0, as theta goes from 0 to theta equals 2 pi. Rho squared sine phi shows up because it's part of the dv, but when we go to integrate, it's going to have to get integrated along with the 1. So dr, d phi, d theta is going last. Those are the 3 d's that we have to fill in. Now we got to figure out what r is between and what phi is between. Any questions? How's everybody okay? Everybody remember our overall plan? We set up the dv with the dr, d theta, or d rho, d theta, and d phi. And we got to figure out what all those variables are between. It's the same thing that we were doing with rectangular coordinates. What's x between, what's y between, what's z between? What's r between, what's theta between, what's z between in cylindrical coordinates? It's the same thing that we did way back in single integrals when we had a dx. What's x between? That's all we had to worry about back then. Gosh, those were the days. The integration part was easier because x was just going to be an interval. All we needed was what's x between. But we had to figure out everything in terms of x. And so that was the hard part. Here, the hard part isn't going to be the integration unless there's trig substitution, even though that's our favorite. The tricky part is setting up the intervals. So now we got to think about rho and phi. Remember that our early integrals, our early intervals can depend on upcoming variables. So if I put either of these two integrals can involve theta, because theta is an upcoming integral. But if I find out that rho is going to be dependent on the value of phi, like we're gonna, then we know that that rho is going to have to be our first integral. If rho depends on phi, then rho will have to be our first, and phi will be our second. If phi depends on rho, which we're not going to find out, then I'd have to switch that around. So in a dx dy dz integral in rectangular coordinates, if we're going to write y as a function of x, the dy integral has to go before the dx integral. Because early integrals can depend on upcoming variables. But if rho depends on phi, I can't put that one in the middle because phi has already gone. So that would mean if rho depends on phi, like it's gonna, then rho is going to have to go first. Let's see why that is going to be the case. Looking at our side view, we can see that phi only cares about this triangle. But rho is different all the way across. So here, when phi is equal to 0, rho is equal to h. When phi is equal to 0, rho is equal to h. Then we start making a triangle. Then as phi slides out, since the top of our cone is flat, Spherical coordinates, it's like, oh, dude, why are you handing me flat stuff? I'm terrible at flat stuff. You're like, oh, shut up. We've all been through trig. Actually, don't be so mean to your spherical coordinates. Just that's it. Just don't be so mean to the spherical coordinates. So if rho was constant, then this would be higher, and we'd see this circle passing through phi. But since we're flattening off the top of our cone, we're going to have different values of rho, and they're going to depend on the angle phi. So here, when phi is equal to 0, rho is equal to h. And then we're going to start building this right triangle, where rho is going to be the hypotenuse, and we're going to have a and h over here. So when we get to this angle out here for phi, that angle we can write in terms of a and h only. We don't have to worry about rho. We can write that in terms of opposite and adjacent. So we'll just do tangent inverse. Tangent is opposite over adjacent, right? So we'll do tangent inverse, or tangent of phi is a over h. So phi is tangent inverse of a over h. We can figure out what phi is at that point without worrying about the value of rho. Remember, a and h are both constants. They're the radius and the height of the cone, respectively. So we just need phi to go from 0 straight up the z-axis down to the angle tangent inverse a over h. That will give us this side view. So phi is between constants. So it looks like d phi is going to be my middle integral. It also looks like, since phi and theta are both just intervals, I could have switched that order if I want. But rho is going to have to go before phi. So the way I've set it up here, rho is going to have to go first. Notice that when phi is equal to 0, rho is equal to h. And then as phi increases, so does the value of rho. The points along this top edge, they get farther away from the origin as we get farther away from the z-axis. So that when phi gets to tangent inverse of a over h, rho, I gotta pick a typical value of phi. And I got to write rho as a function of phi. I can't just use the last one. So I pick a typical value of phi, and I write an expression for rho in terms of phi. So it looks like rho is going to start off at h. Now, in this right triangle, rho is the hypotenuse. The only other constant that we have is the height, because a is way out here, and I'm not using all of that. But throughout this whole sweep, as phi goes from 0 to tangent inverse of a over h, the side opposite phi is all different. The hypotenuse is changing. That's what we're looking for. But this h is constant. Adjacent is constant. So I could say that so I'm going to use, since I want the hypotenuse and I have a nice constant adjacent side, I'm going to use cosine. So we're going to say that I didn't leave myself enough space, which is typical. We're going to say that cosine of phi is opposite, sorry, adjacent over hypotenuse. And I just want to rearrange this so rho is a function of phi. So rho is going to be h over cosine phi, or h secant phi. Since rho is being written as a function of phi, the d rho will have to go before the d phi, but the d phi and the d theta can go in whatever order they want. So I guess I could have put d theta first, d rho second, and d phi third. I guess I could do d rho, d theta, and d phi, or I could do this one that we did. Any questions? There's a lot of shenanigans that we had to incorporate because we're using spherical coordinates, and one of the sides of our cone is flat. That top piece of the cone is flat. Any questions? Is everybody okay? No one committed to an answer. That is correct. Usually when I say, is everybody okay? People just tend to just say, oh yeah, everything's fine. Even when it's not fine. You know what I mean? It's like we say stuff just to kind of like move things along and smooth things out. I don't know if this is an American thing or if this is a human thing, or we're just trying to be polite. Does this make sense? And everyone's like, oh yeah, it's fine. Even though it's totally not okay. And people are all like super confused. I think the student mentality, this is just based on my experience. The student mentality is like, oh, it's not okay, but I'm going to try to fix it later. When I'm on my own, and the person that supposedly knows what they're talking about is not in the room anymore. Which doesn't seem like a great idea, but it is like the student mentality. You know what I mean? You're like confused in class, and teachers are like, oh, are there any questions? And you're like, oh, yeah, but I don't want to ask you. So I get it. I mean, you know, I don't want to talk to me either. I've heard my voice, like a recording of it. And it's all different. So, yeah, I get it. And at least this class is not like all about lying to me. It's like, oh, yes, we totally understand what you're talking about. I'm like, oh, that's awesome. They all understood what I was talking about the first time. That's excellent. Then we have a quiz tomorrow, and you're like, oh, why did everybody flunk the quiz? They said it was okay. I'm just kidding. There's not a quiz tomorrow. Thought I'd look at that flash antenna. Any questions? Sometimes it is just you need to sit with the stuff and think about it for a while. One of the important steps in understanding stuff and thinking about stuff is not thinking about stuff. You need to put some time between now and when you look at this later on. and your subconscious will be working on it and kind of sorting things out. You kind of got to let that happen. Yeah, so in the chat, I don't know what to ask. Sometimes that is absolutely the trouble with asking questions. So I'm like, are there any questions? And you're like, oh, yes, but I don't know what it is yet. So true. But that's why we don't cover a topic and then immediately have a quiz on it. It's like, well, here's some stuff. Think about this. And then at a later date, we'll ask some questions about it. Here's something to put things into perspective. Go back to your notes and find out the things that you were confused on when we first talked about it. Maybe in week 5 on Wednesday. You're like, oh yeah, I made a note here that this shit didn't make any sense. And then see if it makes sense now, whether you've worked on it or not. Like, wait a second, that was that one homework, and I did figure that out. And then that will remind you that, yeah, everything's confusing the first time you see it, but then it just becomes natural. Any questions? It's like driving. You're coming up to a turn. How do you know? How do you know how much to turn the wheel? The answer is you just turn it enough. And then a new driver would say, well, how do you know when enough is enough? And I was like, well, you'll just know. Think about all the calculus that happens when you're out, just even walking around. Something you've been, when do people learn how to walk? Like 2? Since you've been learning to walk in crowds, not just like the first steps, because you're really bad at it at the beginning. And it's really confusing. But just think about walking around campus, how natural it is to do all that calculus automatically. I said that you're doing calculus automatically, instinctively, because calculus is calculating your position, your velocity, and your acceleration. And you can see yourself walking and another person walking on paths, and you can tell if we both continue on this path, we are going to be at the same place at the same time. That means that we will be bumping into each other, and we want to avoid that. And you do this by saying, I'm moving at a constant velocity, and here's my position. That person also appears to have a constant velocity, and you look at their position, and you make those calculations just automatically, and you can tell that you're going to bump into each other. And so you alter course. So you go in and apply some acceleration. You take the derivative of your velocity and you figure out some acceleration to change your velocity, to either speed up to go so that you pass in front of that person, or slow down to pass behind that person. Sometimes they do the same thing. You both start slowing down, then you both start speeding up until one of you just says, all right, velocity equals 0, wait for them to pass, then velocity is, and then you apply some acceleration again. All this calculus is happening automatically. You're not thinking about it. You're not making calculations. You're just figuring out. This system of differential equations, you're just solving it as you're walking along. And everybody does this. At this point in your mathematical career, you're on the verge of learning how to actually make the calculations, but this is just taking instinct and putting math on things that you already understand. That makes sense? Calculus is instinctual. You already know. And like these angles, applying angles to things like X and Y coordinates, you're doing the same kind of thing. You want to take your XY direction and you want to put this curve into it when you're driving. Not only are you doing all these calculations automatically, you're translating them to the vehicle that you're sitting in. I know that you have to slow down to take this corner. And if you drive different cars, you know that in one car, you have to slow down a lot more than another car. I know if I take certain turns in my normal daily, I cannot use that velocity when I'm driving in my dogmobile, because the dogmobile will straight up fall over. I don't think it would actually fall over. I think it would just understeer out to oblivion. So I don't really want to test that theory. And you do all this automatically. It's not like you look up some menu in your vehicle's infotainment system and says, this is the maximum velocity for a turn of this radius. You just kind of automatically do it. For the most part, you dramatically undershoot how fast you could take the curve. I think someone said once, when someone's driving, if it's a decision between like a half a G and driving into the ditch, we tend to just drive into the ditch. But I don't know. I'm gonna have to watch more idiots in cars on YouTube. Any questions? All right, so here we have an integral for the volume of a cone. If we wanted to make sure that we got 1/3 pi a squared h, we would just have to start integrating rho. Notice that our dv had some rho in it, so we would get 1/3 rho cubed sine of phi, and then we would evaluate that from h to h secant of phi. And now we're going to be really unhappy because we're all, dude, that's going to be a secant cubed that we have to integrate. Oh, yeah, it's going to be a secant cube. That's going to be, but then we're going to think about the other integrals that we had to do. Integrals of odd powers of secants without tangents was one of the types of integrals that showed up when we were doing trigonometric substitutions. There were two integrals that showed up when we were doing integration by doing trigonometric substitution. That were the problem ones. Even powers of cosine without sines, odd powers of secants without tangents, because you have even powers of cosines with no sines. That means you had to do something else. You couldn't just do regular substitution. If you have cosine, even powers of cosine, but you have an odd power of sine somewhere, you just do substitution. If you've got odd powers of secants, but there's a tangent, you just do substitution and it's no trouble. It's those two cases, even powers of cosines and odd powers of secants, where you had to do something weird for that stage of the integration. So this is clearly one of those times where you end up with odd powers of secants. Any questions? Oh, wait, you get a tangent because there's a sine over cosine. I almost forgot the sine of phi. Maybe it's just going to be substitution. Maybe I should have put that on the schedule today to actually do this integral. So I'm like, secant cubed, I don't want to do that. Then I forgot about the sine. But then that's a reason to take it off the schedule, because y'all can do this one. All right, think about this construction, about how we built this integral and why we had to build the integral this way. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.